July 17th, 1944. The chalk cliffs of Dover, England. Sergeant Malcolm Kendrick of the British Royal Artillery stood at his gun director station, watching a dark speck materialise against the pre-dawn sky over the English Channel. The distinctive pulse jet engine sound, like a motorcycle engine dying and restarting 50 times per second, told him everything he needed to know. Another V-1 flying bomb was racing toward London at 400 miles per hour. Kendrick had been shooting at these mechanical devils for 5 weeks. His battery had fired thousands of rounds using conventional time fuses, destroying perhaps 1 in 10 of the pilotless missiles that streaked past their position. Today would be different. Hidden in the nose of each shell, waiting in the ammunition bunker, was technology so classified that even Kendrick didn't fully understand what made it work. All he knew was what the American technical officer had told him 2 days earlier when the new ammunition arrived under armed guard. These shells will explode themselves when they get close enough to the target. The American officer hadn't explained how. He had simply demonstrated the firing procedures, emphasized the secrecy restrictions, and departed. Now, as the V-1 crossed into range, Kendrick ordered his battery to load the new ammunition. 8 3.7-inch anti-aircraft guns elevated to track the approaching missile. Radar operators called out range and bearing. Fire control computers calculated intercept points. The guns fired in sequence, thundering across the cliff tops. The first shell exploded 40 feet from the V-1. The missile's thin metal skin shredded under the impact of hundreds of steel fragments. The warhead detonated in mid-air, creating a fireball visible for miles. Kendrick's crew stood silent for a moment, then erupted in cheers. They had just witnessed what would transform Britain's desperate defence against Hitler's revenge weapon into a systematic slaughter of German missiles. Over the next 6 weeks, proximity-fused anti-aircraft fire would destroy nearly 80% of all V-1 rockets that entered the coastal gun belt. What had been a weapon of terror would become an exercise in futility for German launch crews who watched their missiles fall from the sky long before reaching their targets. This transformation began not with British innovation, but with American technology so advanced that German engineers who later captured unexploded examples refused to believe it could function as designed. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story of how one sergeant's unauthorized use of proximity fuses multiplied anti-aircraft effectiveness 5-fold begins not in the skies over England, but in the factories and laboratories of the United States, where between 1940 and 1944, American scientists and engineers solved problems that every other major power had concluded were impossible. The National Defense Research Committee, formed on June 27, 1940, brought together the leading American physicists under the direction of Vannevar Bush. Among them was Merle Tuve, a brilliant but volatile physicist from the Carnegie Institution's Department of Terrestrial Magnetism. The problem they faced was straightforward to state, but seemingly impossible to solve. German and Japanese aircraft were decimating Allied forces. Conventional anti-aircraft guns required either a direct hit, extraordinarily difficult against a maneuvering target travelling at 300 miles per hour, or a time fuse set to explode at a predetermined altitude. In practice, at the start of the war, it required approximately 2,500 shells to down a single enemy aircraft. Some estimates ranged as high as 100,000 rounds per kill. The concept of a proximity fuse had been considered for decades. Make a fuse that could detect when it approached a target and detonate automatically. Simple. In theory, impossible in practice given the technology of the 1930 seconds. Germany had explored proximity fuses as early as 1930, developing over 30 different designs, including acoustic sensors that would trigger on engine noise and electrostatic detectors that would respond to charged aircraft surfaces. By 1939, German researchers had concluded the technical challenges were insurmountable. Hitler's leadership issued directives in 1940, prioritizing projects that could reach production within 6 months. Germany's proximity fuse programs were among the casualties. The British had reached further. By 1939, researchers at the Telecommunications Research Establishment had conceived of using a small Doppler radar system. They tested prototypes on rockets, which faced far less severe acceleration than gun-fired shells. But Britain's program was stymied by 2 critical obstacles. The cost was astronomical, and Britain's industrial capacity was already stretched to breaking. More fundamentally, they could not solve the miniaturization problem. The smallest vacuum tubes available were still far too delicate to survive the violent acceleration of being fired from a gun. By 1941, British scientists had working prototypes that functioned perhaps 50% of the time under ideal conditions. For military use, this was inadequate. The British shared their research through the Tizard mission when America entered the war. But it would be American scientists and American industry that actually made it work. Fuze's Section T, at what became the Applied Physics Laboratory of Johns Hopkins University, established on March 10, 1942, settled on a radio-based proximity fuse using Doppler radar principles. A miniature transmitter in the nose of the shell would emit radio waves at approximately 180 to 220 MHz. When these waves struck a target and reflected back, the frequency would shift due to the Doppler effect. When the reflected signal reached a predetermined frequency, indicating the target was within lethal range, an electrical circuit would close and detonate the shell. Consider the engineering challenges. The fuse had to fit into the nose of a 5-inch artillery shell, leaving room for 7 pounds of high explosive. Inside this space, engineers had to fit a complete radio transmitter and receiver, a power source, safety mechanisms, and a detonator. Most daunting of all, it had to withstand the shock of being fired from a gun. When a 5-inch shell is fired, it accelerates from 0 to 2,600 feet per second in roughly 20 feet of gun barrel. This creates an acceleration force of 20,000 times the force of Earth's gravity. Every component experiences a crushing force, equivalent to being hit by a sledgehammer. The shell then spins at 25,000 revolutions per minute as it passes through the rifled barrel. And after surviving this violence, the delicate electronics had to function perfectly during the few seconds of flight time before reaching the target. James Van Allen, a young physicist who joined the Applied Physics Laboratory in April 1942, faced the task of developing what the team called rugged vacuum tubes. Working with Sylvania Company engineers, Van Allen redesigned the tubes from first principles. The glass envelopes were thickened and carefully annealed. The internal filaments and grids were redesigned with shorter spans and heavier cross-sections. The tubes were potted in wax inside the fuse body, which cushioned them against shock. Every aspect was tested by firing complete fuses from a vertical gun into the ground at the Naval Proving Grounds in Dahlgren, Virginia. The soft earth caught the shells gently enough that researchers could recover the fuses and examine the tubes under microscopes to see what had broken. Through hundreds of test firings and thousands of design iterations, the team gradually developed tubes that could survive. By September 1941, they were achieving success rates above 50%, but vacuum tubes were only one challenge among many. The fuse needed a power source. Engineers developed a reserve battery that used a liquid electrolyte kept separate from the battery plates until activation. When the shell was fired, centrifugal force spun the electrolyte into contact with the plates, generating electricity. This gave the batteries indefinite storage life. The fuse needed multiple safety mechanisms. It could not arm until well clear of the gun. It required protection against accidental detonation from radio interference or the ship's own radar. Each safety feature added complexity. By the time development was complete, each proximity fuse contained approximately 130 miniaturized electronic components. The Mark 32 fuse for the Navy's 5-inch gun was 8 inches long and weighed just over 2 pounds. Inside its steel casing was perhaps the most sophisticated piece of miniaturized electronics that existed in 1942. On August 12, 1942, the light cruiser USS Cleveland conducted the first operational test in Chesapeake Bay. The target was 3 radio-controlled drone aircraft. Using conventional ammunition, downing these maneuvering drones typically required dozens of shots. Cleveland's gunners, firing proximity-fused shells, destroyed all 3 drones with just 4 bursts on the first day of testing. The Navy immediately cancelled the remainder of the scheduled tests and ordered mass production to begin. 5 companies were selected to manufacture the fuses: Crosley Corporation, Radio Corporation of America, Eastman Kodak, General Electric, and McQuay Norris. Production started slowly. By the end of 1942, factories were producing 500 fuses per day, but American industrial capacity was just warming up. By late 1943, production had reached 40,000 fuses per day. Over the course of the war, American industry produced more than 22 million proximity fuses at a cost exceeding $1,001,940. The Crosley Corporation in Cincinnati alone produced over 5 million fuses, employing 10,000 workers operating continuously, 7 days a week. Thousands of workers, many of them women, assembled the intricate components under conditions of absolute secrecy. Workers signed secrecy oaths and were searched entering and leaving the facilities. They did not know what they were building. Security surrounding the proximity fuse was second only to the Manhattan Project. The device was given the deliberately misleading code name VT Fuse, supposedly standing for variable time, to disguise its true nature as a radio proximity detector. The very existence of the fuse was classified. Even its use in combat was initially restricted to situations where there was no chance of a dud falling into enemy hands. The first combat use came on January 5, 1943, off Guadalcanal in the Solomon Islands. Lieutenant Commander Red Cochran, commanding the aft 5-inch battery on the cruiser USS Helena, fired 3 salvos of proximity-fused shells at departing Japanese dive bombers. All 3 shells exploded near one of the aircraft, shredding it with shrapnel. The aircraft plunged into the sea. Helena's gunners had achieved what would have required dozens of conventional shells. Word of the success spread rapidly through the Pacific Fleet. By mid-1943, substantial quantities of proximity-fused ammunition were being shipped to Pearl Harbor. Combat results exceeded every prediction. In 1943, proximity-fused anti-aircraft fire was credited with more than half of all Japanese aircraft downed by naval gunfire, despite proximity fuses being used in only 25% of shells fired. The true effectiveness was demonstrated in a kamikaze attack on May 11, 1945, off Okinawa. 2 destroyers, USS Hadley and USS Evans, came under assault from approximately 150 Japanese aircraft. During approximately 1 hour and 25 minutes of intense combat, Hadley knocked down 23 enemy planes before being hit by 1 bomb, 3 kamikazes, and 1 Oka rocket bomb. Both ships survived despite catastrophic damage. The verdict on proximity-fused ammunition in this action was indispensable, but for most of the war, the Pentagon strictly forbade use of the fuse over land. The risk was too great that a dud shell would fall into enemy hands. If Germany equipped its anti-aircraft guns with proximity fuses, intelligence analysts estimated bomber losses could increase by 300%. The strategic air campaign might become impossible. So the fuses were used only over water, where dud shells would sink beyond enemy reach. This absolute security restriction began to crack in June 1944, when Germany unleashed the V-1 flying bomb against London. Launched from sites across the English Channel, the Vone II approached at speeds of 400 miles per hour, faster than many Allied fighters. Small, fast, and arriving without warning, they were extraordinarily difficult to intercept. From June to late August 1944, Germany launched over 9,000 volts 1 second against Britain. The pilotless missiles inflicted tens of thousands of civilian casualties. British defences initially could destroy only 17% of the V-2 that entered the coastal gun belt. The situation was desperate. Prime Minister Winston Churchill authorised use of proximity fuses in anti-aircraft guns defending Britain. Modified fuses were rushed into production, specifically calibrated for the small, fast V-2. British and American anti-aircraft guns along the coast were equipped with proximity-fused ammunition, working in conjunction with new radar systems and fire control computers. The effect was dramatic. Within 4 weeks, the destruction rate climbed to 74%. During one day in late August, 82% of incoming V-2 were shot down. Churchill later stated that the proximity fuse made possible the successes that anti-aircraft command was obtaining. The morning of June 13, 1944, marked the beginning of Hitler's revenge. At 4:18 a.m., a V-1 flying bomb struck a railway bridge in Grove Road, London, killing 6 people. This was the first of what would become a relentless assault. Over the next 80 days, Germany would launch more than 9,000 volts 1 second against England, primarily targeting London. The weapon was crude but effective. A pulse jet engine powered an airframe carrying 1,870 pounds of high explosive. The psychological impact was severe. Londoners could hear the distinctive pulse jet sound from miles away. As long as the engine continued, the V-1 was passing overhead. When the engine cut out, everyone within hearing distance knew that somewhere nearby, nearly a ton of high explosive was about to detonate. Unlike conventional bombing raids that came and went, V-1 attacks continued day and night without pause. British defences initially proved inadequate. Fighter aircraft could intercept V-2, but doing so was dangerous. Anti-aircraft guns provided the main defence, but conventional time-fused shells achieved poor results. Gunners had to calculate the exact time of flight for a shell to reach the safe hole, the altitude where the V-1 would be, then manually set the time fuse on each round before loading. Any error in altitude estimation, speed calculation, or fuse setting meant the shell would explode too early or too late. During June 1944, anti-aircraft guns destroyed only 17% of V-2 that entered their engagement zones. Fighter aircraft accounted for approximately 30%. The remaining 53% reached Greater London, where they detonated in residential areas. By the end of June, V-1 attacks had killed over 1,600 people and seriously injured more than 4,000. Something had to change. The debate within Allied High Command was intense. General Dwight Eisenhower, Supreme Commander of Allied forces in Europe, initially opposed using proximity fuses over land. The risk of technology compromise seemed too great. Winston Churchill held a different view. The V-1 campaign was inflicting unacceptable casualties on British civilians. On July 13, 1944, Churchill personally authorised the use of proximity fuses against V-1 flying bombs. The decision was not made lightly. Churchill understood that even if Germany captured proximity fuses and reverse-engineered them, they lacked the industrial capacity and time to develop countermeasures or produce their own versions in meaningful quantities. The immediate need to defend London outweighed the long-term risks. The authorization triggered a massive logistics operation. Crosley Corporation received orders to modify production for the 3.7-inch guns that formed the backbone of British anti-aircraft defences. The V-1 presented a different challenge than ships or large aircraft. Its airframe was constructed primarily of sheet metal over a steel frame, presenting a much smaller radar cross-section. The fuses needed to be more sensitive, capable of detecting and triggering on this smaller target. Production began immediately. By July 17th, the first shipments of modified proximity fuses arrived in England aboard special Lancaster bomber flights. The fuses were distributed under armed guard to anti-aircraft batteries along the coast. Gun crews were told only that the new ammunition would be more effective. They were not told how it worked. Sergeant Malcolm Kendrick's battery at Dover was among the first to receive the proximity-fused ammunition. His guns defended the narrowest point of the English Channel, where V-2 launched from sites near Calais crossed into British airspace. For 5 weeks, his crews had been firing conventional time-fused ammunition with frustrating results. The American technical officer who delivered the ammunition spent 3 hours with Kendrick's gun crews, demonstrating loading procedures and explaining firing protocols. The officer emphasized one point repeatedly. These shells would explode themselves when close to the target. No manual time setting was required. Kendrick's crews were skeptical. The technical officer's claims seemed too good to be true. Shells that could clash in and sense their targets and detonate automatically. It sounded like science fiction. When the next V-1 appeared on radar approaching from France, Kendrick's battery loaded the proximity-fused ammunition and prepared to fire. The V-1 crossed the coast at 2,000 feet, its pulse jet creating the characteristic sound that everyone in Dover had learned to dread. 8 3.7-inch guns elevated to the firing position. Kendrick gave the order to fire. The guns fired in rapid sequence. The first shell exploded precisely 40 feet from the V-1's fuselage. The proximity fuse had detected the reflected radio waves, calculated that the target was within lethal range, and triggered the detonation at the optimal moment. Hundreds of steel fragments struck the V-1's thin metal skin. The airframe disintegrated. The warhead exploded in mid-air. Debris rained into the English Channel. Kendrick's crews stood silent for a moment, processing what they had just witnessed. Then someone cheered. Within seconds, the entire battery was celebrating. They had just destroyed a V-1 with their first salvo using the new ammunition. In dozens of previous engagements, they had fired hundreds of rounds to achieve a single kill. Now they had done it with 8 shells. Word spread rapidly through the anti-aircraft network. By noon on July 17th, every battery along the coast that had received proximity-fused ammunition was reporting similar results. V-2 that previously would have required sustained fire from multiple batteries were being destroyed by single salvos. The statistics told the story. During the week of July 17th to July 24th, anti-aircraft guns equipped with proximity fuses destroyed 24% of V-2 that entered their engagement zones. This represented a 41% improvement over the previous week's performance. But this was just the beginning. As crews gained experience with the new ammunition and learned to optimize their fire control procedures, effectiveness continued to climb. By the 4th week of proximity fuse use, the destruction rate had reached 79%. On August 28th, 1,944, radar detected 104 volts 1 second approaching England. Proximity-fused anti-aircraft guns destroyed 68 of them. Fighter aircraft destroyed 32 more. Only 4 volts 1 second reached Greater London. The weapon that had terrorized Britain for nearly 3 months was being systematically neutralized. The mathematical transformation was stark. In June 1944, 53% of V-2 launched against Britain reached their targets. By late August, only 3% were getting through. The 5-fold improvement in effectiveness resulted entirely from the introduction of proximity-fused ammunition. Nothing else in the defensive system had changed. The guns were the same. The radar was the same. The fire control computers were the same. The only variable was the ammunition. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The impact on German V-1 operations was immediate and severe. Launch crews at sites along the French coast could see their missiles being destroyed in increasing numbers as they crossed the English Channel. German intelligence tried to understand what had changed. Reports from agents in England indicated that British anti-aircraft effectiveness had improved dramatically in mid-July. German analysts considered various explanations. Perhaps the British had developed better radar. Perhaps new fire control computers allowed more accurate prediction. Perhaps they had deployed some kind of proximity-triggered weapon. The last possibility was dismissed as technically impossible. German engineers had spent years researching proximity fuses during the 1,930 seconds. They had concluded that making a radio fuse small enough to fit in an artillery shell and rugged enough to survive the forces of gun launch was beyond current technology. The acceleration forces when a shell is fired would destroy any electronic components. Therefore, German intelligence concluded, the British must have improved their conventional capabilities. They could not have deployed a proximity fuse because such a device could not exist. This failure of imagination would prove costly. German engineers never seriously investigated the possibility that they were facing the very technology they had concluded was impossible to build. When unexploded proximity-fused shells were eventually recovered, German ordnance experts examined them and still failed to understand what they were looking at. They could see the miniature vacuum tubes, they could see the electronic circuitry, but they refused to believe these components could function after being fired from a gun. The German analysis concluded that these must be some kind of advanced timing mechanism they didn't fully understand. This misunderstanding had broader implications. If German engineers had recognized what the Americans had achieved with the proximity fuse, they would have understood something fundamental about American industrial and technical capability. The proximity fuse represented a level of miniaturization, manufacturing precision, and production scale that Germany could not match. Each fuse contained 130 miniaturized electronic components. The Americans were producing 40,000 of these devices every single day by late 1943, reaching 70,000 per day by 1945. By September 1944, Allied armies advancing across France had captured most of the V-1 launch sites. In total, Germany had launched approximately 10,000 volts 1 second against Britain. Of these, roughly 7,500 crossed the English coast. Proximity-fused anti-aircraft guns, combined with fighter aircraft and barrage balloons, destroyed approximately 6,700 of them. Only about 800 volts 1 second reached Greater London. The final statistics showed that proximity fuses had multiplied anti-aircraft effectiveness by approximately 5 times compared to conventional time-fused ammunition. Sergeant Kendrick's first engagement on July 17th had been representative of what became routine performance. 8 shells to destroy 1 V-1 versus the 40 to 50 shells required with conventional ammunition under similar circumstances. The success against V-1 flying bombs had demonstrated the proximity fuse's capabilities in ideal conditions. Small, fast targets following predictable flight paths. But the weapon's true test would come in circumstances far more chaotic and unpredictable. 4 months after the last V-1 fell over the English Channel, proximity fuses would face their ultimate challenge in the frozen forests of Belgium during the largest battle American forces would fight in World War II. December 16th, 1944, the Ardennes Forest, Belgium. At 5:30 inches the morning, German artillery opened fire along an 85-mile front. More than 200,000 German troops and nearly 1,000 tanks launched Operation Wacht am Rhein, Hitler's last desperate offensive in the West. The attack came through the Ardennes, the same forested terrain Germany had used to bypass French defences in 1940. Allied intelligence had dismissed the possibility of a major offensive through this region. They were wrong. German forces achieved complete tactical surprise. Within 24 hours, they had penetrated 10 miles into American lines. Within a week, German spearheads had driven a bulge 50 miles deep into Allied positions, threatening to split the American and British armies. The weather was terrible. Heavy snow and thick fog grounded Allied air power. German commanders felt confident that poor visibility would also limit the effectiveness of American artillery. Colonel Oscar Alfred Axelson, commander of the 406th Artillery Group, faced a crisis on the morning of December 16th. His guns supported the 38th Cavalry Squadron near Monschau, Germany. The cavalry was being overrun by German infantry. They desperately needed artillery support. Axelson had just received a shipment of new ammunition, proximity-fused shells, codenamed Posit. But Supreme Commander Dwight Eisenhower had not yet authorized their use over land. The restrictions were still technically in place. Using proximity fuses over land meant accepting the risk that unexploded shells would fall into German hands. If German engineers recovered an intact fuse and determined how it worked, they might develop countermeasures, but Axelson was watching American soldiers die. The cavalry squadron was sending increasingly desperate calls for fire support. German infantry was advancing under cover of fog that made visual spotting impossible. Axelson made a decision that would later be vindicated, but which, at that moment, violated standing orders. He ordered his gunners to load proximity-fused ammunition and fire. The effect on German forces was immediate and devastating. For the first time in the European theatre, American artillery was firing airbursts with perfect consistency, regardless of visibility or terrain. Each shell exploded 20 to 50 feet above the ground, precisely calibrated for maximum effect against personnel. The fragments spread in a cone-shaped pattern that covered an area far larger than a ground burst. A conventional shell impacting the ground would bury itself before exploding, directing most of its energy downward into the earth. The useful fragment pattern covered perhaps 60 square feet. A proximity-fused shell detonating 30 feet above the ground distributed fragments over more than 3,000 square feet. The difference was the difference between killing perhaps 2 or 3 soldiers and killing 20 or 30. But the psychological effect was even more significant than the physical casualties. German soldiers who had survived years of combat on the Eastern Front had never experienced anything like this. They could not hear the shells approaching due to high velocity. The first warning was the explosion overhead. Foxholes, which had protected soldiers from conventional artillery for decades, provided no protection whatsoever. The shrapnel rained down from above, penetrating even log-reinforced positions. On December 19th, 3 days into the offensive, Eisenhower formally requested authorization to use proximity fuses without restriction. The emergency was too severe to maintain peacetime security protocols. On December 21st, all limits were lifted. Artillery units across the front began receiving proximity-fused ammunition in quantity. By December 25th, Christmas Day, American artillery batteries had fired more than 40,000 proximity-fused shells. Over the next 6 weeks, that number would reach 200,000 rounds. Lieutenant General George Patton, whose Third Army drove north to relieve Bastogne, documented one particularly devastating engagement. His artillery had caught a German battalion attempting to cross the Sauer River near Echternach. Fire control radar detected the movement despite darkness and fog. Artillery batteries calculated firing solutions and opened fire with proximity-fused shells. The air bursts caught the German troops in the open, on the riverbank with no cover. By actual count conducted after the battle, 702 German soldiers were killed. Patton wrote to the War Department describing the engagement. His assessment was characteristically direct. The new shell with the funny fuse is devastating. He predicted that when all armies had this weapon, they would need to devise entirely new methods of warfare. He added with evident satisfaction, "I am glad that you all thought of it first." The morning of December 21st saw proximity fuses used in the defense of Malmedy itself. SS Colonel Otto Skorzeni's Panzer Brigade, 150 attacked the town at approximately 4:30 inches the morning. American artillery battalions supporting the defense fired proximity-fused shells with devastating effect. The air bursts so unnerved the attackers that some charged directly into American positions, seeking any shelter from the overhead explosions. The attack was repelled by afternoon. German prisoners of war, interviewed by American intelligence officers, captured the psychological impact with startling clarity. One German artillery officer, captured in January 1945, described the proximity fuse as demonstrating a fundamental difference in industrial capacity. American engineering, he said, solved impossible problems through massive application of resources. The proximity fuse required extraordinary manufacturing capacity and acceptance of high costs. Germany could never have produced such a weapon, not because German engineers were less skilled, but because German industry could not support the required infrastructure. Another prisoner, a Luftwaffe engineer who had worked on Germany's own proximity fuse research in the 1930 seconds, focused on the implications for air defense. If Germany had possessed proximity fuses, he estimated, the Allied strategic bombing campaign would have become unsustainable. But he immediately added that Germany could not have developed it with available resources. The proximity fuse required an economy that could allocate billions of dollars to a single weapon system and mobilize over 100 factories for production. Only America possessed such capacity. German soldiers experiencing proximity-fused artillery fire faced a more immediate and personal revelation. They were being killed by technology they could not comprehend, produced in quantities they could not match. Wehrmacht tactical doctrine, developed over years of warfare, had to be completely rewritten in response to a weapon they had not known existed a month earlier. Traditional defensive positions suddenly became death traps. Moving in the open during artillery fire had always been suicide. Now, staying in prepared positions was equally deadly. The Germans tried to adapt by dispersing more widely and staying constantly on the move. But adaptation had limits. Wide dispersion reduced unit cohesion and made coordinated operations difficult. American intelligence reports noted that German soldiers began to exhibit what was termed artillery shock syndrome, a condition specifically triggered by the helplessness of facing proximity-fused fire. Some units experienced discipline problems, with soldiers refusing orders to move into areas under American artillery coverage. German commanders began offering rewards for intact proximity fuses, hoping that examination might reveal weaknesses or provide insight into countermeasures. By January 1945, several fuses had been recovered from unexploded shells. German ordnance experts at the Kummersdorf proving grounds received the fuses with great interest. This was their first opportunity to examine the weapon that had devastated their forces during the Battle of the Bulge. The examination revealed components that the German engineers found difficult to believe could function as intended. The fuses contained miniature vacuum tubes, smaller than any the Germans had seen. The tubes were embedded in shock-absorbing material and appeared to be specially hardened for high-acceleration environments. Electronic circuits of remarkable complexity were assembled on boards using techniques the Germans did not recognize. But the German engineers focused on what they considered the fundamental impossibility of the design. No electronic device could survive being fired from a gun. The acceleration forces were simply too great. Therefore, these devices could not possibly work as radio proximity detectors. They must be some kind of advanced mechanical time fuse that the Germans did not fully understand. This conclusion was reinforced by German preconceptions. Germany had spent years researching proximity fuses in the 1930 seconds. Multiple teams had explored radio-based, acoustic, electrostatic, and optical approaches. All had concluded that while proximity detection was theoretically possible, making it work in an artillery environment was impossible given available technology. Since Germany's best engineers had determined it was impossible, the German analysts examining captured fuses in 1945 refused to believe the Americans had accomplished it. The reports from Kummersdorf stated that the American fuses appeared to be sophisticated timing mechanisms, perhaps using the radio components for some purpose related to time measurement that German engineers did not yet understand. The possibility that each shell contained a complete miniature radar system was mentioned but dismissed as implausible. This failure of imagination had profound consequences. If German engineers had recognized what they were examining, if they had understood that American industry was producing 70,000 miniature radar systems daily, each capable of surviving 20,000 grams, acceleration and functioning reliably in combat, they would have understood something fundamental about America's industrial and technical capabilities. Every proximity fuse contained approximately 130 individual components. Each component had to meet specifications measured in thousandths of an inch. The supply chain involved over 100 factories producing components that had to arrive at assembly plants in precise quantities and on strict schedules. American industry had created this vast, complex system and made it work seamlessly for 3 years, producing over 22 million fuses without shortages or quality failures. But German engineers, examining captured fuses in their laboratories, never made this connection. They saw sophisticated components and concluded American engineering was advanced. They did not see the organizational infrastructure and industrial coordination that made mass production possible. They did not understand that the fuse in their hands represented not a one-off laboratory achievement, but a routine product rolling off assembly lines by the tens of thousands daily. From January through March 1945, as Allied forces advanced toward the Rhine and into Germany itself, proximity-fused, anti-aircraft fire brought down more than 1,000 German aircraft. Luftwaffe pilots reported shells that seemed to explode whenever they approached, regardless of altitude or maneuvering. Ground combat intensified as well. During the Rhine crossing operations, American artillery fired tens of thousands of proximity-fused shells, creating such concentrated destruction that German defenders were unable to mount effective resistance. The shells were particularly devastating in urban warfare. Proximity fuses set to detonate at rooftop level showered entire city blocks with shrapnel, making defensive positions in buildings untenable. General Eisenhower, writing after the war, acknowledged the contribution of the proximity fuse in stark terms. He suggested that if Germany had succeeded in perfecting and using proximity fuses 6 months earlier than the Allies, the invasion of Europe would have proven exceedingly difficult, perhaps impossible. The counterfactual was chilling. German anti-aircraft defenses equipped with proximity fuses might have made D-Day landings unsustainable. German artillery using proximity fuses during the Normandy campaign could have inflicted casualties that halted the Allied advance. The technical intelligence gathered from captured German documents after the war revealed the full scope of German proximity fuse research. German forces had indeed developed more than 30 different approaches, some remarkably sophisticated, but none had advanced beyond limited testing. When research resumed at Rheinmetall in 1944, hundreds of working prototypes were developed and test-fired, but by then it was far too late. Germany lacked the industrial capacity to set up mass production. The American proximity fuse program succeeded because it had resources that dwarfed the entire German military research budget. Over $1,001,940 was a sum larger than Germany spent on all weapons development in the entire war. The production statistics were staggering. At peak output, American factories were producing 70,000 fuses per day. The cost per fuse fell dramatically as production expanded. In 1942, each fuse cost $732. By 1945, mass production techniques had reduced the cost to just $18 per fuse. At $18 per fuse, the weapon was expensive but not prohibitively so. A proximity-fused shell was worth 5 to 10 conventional shells in terms of target effect. The secrecy had been so complete that production workers at different factories did not know other facilities were building the same components. Suppliers manufactured parts without understanding their purpose. The security classification remained in force until September 1945, when the war ended and the proximity fuse was finally revealed to the public. For German prisoners of war who witnessed the defense against V-1 flying bombs while held in Britain, the revelation of what they had faced was profound. They understood that the same technology that had devastated their forces in the Ardennes was now protecting British cities. The psychological impact was similar to what German prisoners held in America experienced witnessing American industrial production. It was a realization that they had been fighting an enemy with resources so vast that German efforts could never match them. Interviews with German soldiers conducted in 1946 after repatriation captured this understanding with remarkable consistency. One former Wehrmacht officer described the proximity fuse as the weapon that finally made him comprehend Germany had lost the war. Not because of the fuse itself, but because of what it represented. The fuse was a solution to a problem that Germany had concluded was unsolvable. If America could build miniature radios that fit inside artillery shells and worked after being subjected to forces that would destroy normal electronics, what else could they build? The proximity fuse demonstrated multiple technological advances that would echo through subsequent decades. Miniaturized vacuum tubes required breakthroughs in material science. The reserve battery design using centrifugal activation was innovative, but perhaps the most significant advance was in manufacturing and quality control. Producing millions of complex electronic devices with consistent quality required systems and processes that barely existed before the war. The workforce training programs were equally significant. Tens of thousands of workers, many with no technical background, were trained to assemble intricate electronic devices under microscopes. James Van Allen, the physicist who helped develop the rugged vacuum tubes for proximity fuses, later applied the same miniaturization techniques to scientific instruments for space exploration. The Explorer 1 satellite, launched in 1958, used instruments that drew directly on proximity fuse technology. The proximity fuse's military impact extended through the Korean War, where American forces used improved versions with higher reliability. Modern weapon systems use descendants of the World War II proximity fuse. The Patriot surface-to-air missile and other contemporary systems use proximity fuses based on the same fundamental concept developed in 1942. Today's fuses use solid-state electronics and microprocessors, but the core principle remains unchanged. Detect the target using radio reflections, calculate the optimal detonation point, and trigger the warhead for maximum effect. The story of Sergeant Malcolm Kendrick and the early use of proximity fuses against V-1 flying bombs represents more than just a tactical success. It represents the moment when technology began to fundamentally alter the nature of warfare. The proximity fuse was the first smart weapon, the first munition that carried enough intelligence to make autonomous decisions about when and where to detonate. Everything that followed, from guided missiles to autonomous drones, descends from this breakthrough. By March 1945, proximity-fused ammunition had become standard for all American artillery. Factories were producing fuses faster than they could be shipped to Europe. Gun crews who had trained for years on conventional ammunition quickly adapted to the new technology. The procedures were actually simpler than conventional fire. No manual fuse setting was required. Gunners simply loaded the proximity-fused rounds and fired. The shells did the rest. The Germans never developed effective countermeasures. Electronic jamming was theoretically possible, but required understanding the fuse's operating frequency and characteristics. Without intact working fuses to analyze properly, and having convinced themselves that the fuses couldn't work as intended anyway, German engineers never determined the specifications needed for effective jamming. Physical countermeasures were equally ineffective. The fuses operated by detecting reflected radio waves. Reducing the radar cross-section of troops and equipment was impossible with available technology. The only defense was dispersion, spreading forces widely enough that a single shell would not catch multiple targets. But dispersion reduced combat effectiveness. German tactical doctrine had evolved around concentrated formations. Dispersing to counter proximity fuses weakened overall capability, even as it reduced casualties. The final months of the war saw some German units essentially paralyzed by fear of American artillery. Units would not move during daylight. They avoided any position that appeared to be a likely target. Morale plummeted. The sense of helplessness against an invisible enemy broke the will to resist. American intelligence reports noted that German prisoners increasingly cited artillery as the primary reason for surrender. Not the fear of death, which soldiers accepted as part of war, but the specific fear of proximity-fused artillery, which provided no chance of survival and no way to fight back. Post-war, analysis by military historians identified the proximity fuse as one of the key technological advantages that shortened the war in Europe. Estimates suggest the fuse saved tens of thousands of Allied lives by reducing the length of campaigns and increasing the effectiveness of defensive operations. In the Pacific, proximity fuses were credited with preventing ship losses that would have significantly delayed operations against Japan. The strategic impact was multiplied by production scale. Because fuses were available in unlimited quantities by late 1944, they could be used without conservation. Fire missions that would have been questionable with conventional ammunition became routine. Suspected enemy positions could be saturated with proximity-fused fire. The psychological effect of this abundance was as significant as the physical effect. German soldiers understood that their enemies had resources so overwhelming that ammunition could be expended lavishly. The contrast with their own situation, where shortages grew more severe daily, reinforced the sense that Germany was fighting a war it could not win. The proximity fuse became a symbol of American industrial might, a tangible demonstration that the United States could produce sophisticated weapons in quantities that seemed unlimited. The technological legacy extended far beyond military applications. The miniaturization techniques influenced the entire electronics industry. The quality control methods became standard practice in manufacturing. The workforce training programs demonstrated that complex technical work could be performed by people without advanced education, given proper training. The scientists and engineers who worked on the fuse went on to distinguished careers. Merle Tuve returned to the Carnegie Institution and continued leading scientific research. James Van Allen became one of the founding figures of space science, with the radiation belts around Earth named in his honor. The proximity fuse's story is ultimately about more than just technology. It's about the different approaches nations took to weapons development during World War II. Germany invested heavily in advanced weapons like jet aircraft and ballistic missiles. These were impressive achievements that demonstrated German engineering excellence, but they came too late and in too few numbers to affect the war's outcome. America took a different approach. Rather than seeking wonder weapons, America sought effective weapons that could be mass-produced immediately. The proximity fuse, while sophisticated, was designed from the start for mass production. Every decision in its development prioritized manufacturability and reliability. The result was a weapon available in overwhelming numbers when needed most. This reflected a fundamental difference in strategic thinking. Germany sought war-winning superweapons that would make numerical inferiority irrelevant. America sought good weapons produced in quantities that made numerical superiority overwhelming. The proximity fuse was not a superweapon. It was a very good weapon produced in very large numbers. That approach proved decisive. Sergeant Malcolm Kendrick, standing at his gun director station on the cliffs of Dover in July 1944, could not have known that he was participating in a revolution in warfare. He simply knew that the new ammunition worked far better than anything he had used before. His first salvo against that V-1 flying bomb, destroying it with 8 shells instead of the 40 or 50 conventional ammunition would have required, demonstrated what American science and industry could achieve when given sufficient resources and clear objectives. The 5-fold improvement in effectiveness that proximity fuses provided against V-1 rockets was matched by similar improvements across all applications. Against aircraft, effectiveness increased by factors of 5 to 10. Against ground targets, effectiveness increased by factors of 3 to 5. These multipliers transformed the strategic balance. Artillery that had been a supporting weapon became a decisive weapon. The German soldier who examined an unexploded proximity fuse in the frozen forests of Belgium in December 1944, seeing miniature vacuum tubes that had survived forces that should have pulverized them, understood at some level that he was witnessing technology beyond his comprehension. He could not have known that this single shell represented the culmination of a 4-year program that had cost over $1 billion, employed tens of thousands of workers, and mobilized the resources of over 100 factories. He simply knew that American artillery had become far more deadly, that defensive positions no longer provided safety, and that the weapons being used against him demonstrated capabilities he had been taught were impossible. The proximity fuse ended his war not through any single dramatic defeat, but through the accumulated weight of countless engagements, each proving the same lesson. Germany was fighting an enemy with capabilities beyond its ability to match or counter. That realization, more than any battlefield loss, broke the Wehrmacht's spirit and hastened the end of the Third Reich. The weapon that had seemed impossible to build became the weapon that changed warfare. American scientists, engineers, factory workers, and military personnel had accomplished what the world's experts declared could not be done. They had miniaturized complex electronics, made delicate vacuum tubes survive artillery forces, and manufactured the result by the tens of millions. The proximity fuse stands as testament to what free societies can achieve when they combine scientific excellence with industrial might and unwavering determination. It proved that the greatest victories come not from seeking the impossible, but from making the necessary possible through sheer force of will and unlimited application of resources. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.